Okay, let's get started. All right, so last Tuesday, I don't believe we got to vector quantization, did we? Does anybody ever heard of that? Okay, I didn't think so. Okay, so we just finished k-means, so we'll go on to vector quantization today. Okay, so k-means is a clustering algorithm. Clustering algorithm means we're going to take a bunch of data points and we're going to group them together, where similar things get grouped together. It is unsupervised, meaning there are no labels. We don't know anything about them other than the feature vector, and we're just finding things that kind of look similar. So we talked about a couple different sort of high-level strategies. But then we talked about k-means, which is one of the most common ones. K-means has two steps. First, you start with some random center points, basically random clusters, but we start with random center points. So let's say they're here and here. And then you assign all the data points to the closest center. So maybe we go with these. And I don't know, these. And then the next step is to recalculate the centers. So now we have the centers up here, and this center, I don't know, is here now. Now, of course, all my examples are well clustered on the first iteration, so we probably wouldn't move points, but if there was a point that was sort of in between here, it might go from this original cluster over to this cluster when you find the new center point. And that's the whole thing with k-means. You just iterate going back and forth until things aren't moving around. The only trick that you need to watch for is if a cluster becomes empty, you want to refill it with one new data point just to create a new cluster that has a single data point, which hopefully will then be close to a bunch of other things and tear another cluster apart. So that's basically classification k-means. So now we're going to talk about one of the big applications of clustering. So clustering, there's a lot of, let's back up a second. There's a lot of problems where we don't have a fixed length feature vector for every data item. For example, we might have a document or a bunch of documents. The documents have words, they're all different lengths. And you can't just stuff those into a classifier without doing some pre-processing to get a feature vector that's a fixed length so that all the items have the same length. So with a document, what we generally do is we come along and we basically look through all the documents. We build up a dictionary, and then for each document, we go and we count the number of times that the words in the dictionary occur in that document. So we do the sort of histogram trick that we looked at on Tuesday, where you would build basically a fixed length vector, which is the count of different words in your vocabulary. So maybe this is that would be a weird document, but doc, I don't know, this is there, and each document would now get a certain count of words. Now, because your dictionary is a fixed size, that means this histogram becomes a fixed size, and that means you can directly stick it into a classifier. Because now every document is just represented by the number of words for each of the dictionary entries. So this is often called bag of features, or bag of words when you're doing documents, but bag of features when you're looking at other things. Now this doesn't just apply to words. Images also have sort of this problem. And while modern image recognition uses a completely different approach from what we're going to talk about, sort of historical image recognition did some different things. So if we were to draw something, let's see, this is what is that? Ah, that was a pretty good elephant. It's probably the best elephant I've ever drawn. I didn't say it was good. It just was the best one. Okay, the ear is kind of broken, but okay. So, assuming this is actually an elephant, you gotta have a tail. Okay. The way vision often worked is they would identify features. So vision would say things like, we can look for eyes, we can look for, I don't know, ears. Generally, they're all the same. We could look for the trunk. We could look for, legs of this shape. We could look for a tail. And then if we had, say, a car, we could look for different features. We'd look for wheels. We'd look for mirrors. We'd look for other things. And that would become the dictionary that we'd use. So you'd have some sort of pre-processing that would go to the image and say, yeah, I see two eyes, I see two wheels, I see, well, not in the same picture, but, I see the elephant feet from my dictionary, that sort of thing. So you would take your dictionary, apply it, create a vector of features where it's just the counts, and you'd use that. So that was kind of a classic image recognition. And you basically get, with images, you basically get a bunch of filters that say, if I take this filter and I compare it against the image, does it occur? And usually you do things like you sweep it through the image and figure out where it occurs and things like that. But we're not going to go into that particular aspect of it. But this is called bag of features. And this is a really powerful approach to anything where it's not a fixed size to start with. It's still used for documents. It's actually hugely competitive with even some of the much more modern techniques for document sort of recognition or processing. It's not used for images as much nowadays, although there still is, in even say a neural net image recognition, there's a layer in there that identifies these blocks of features. And you can actually extract them and see the sort of things that a neural net, a modern image recognition system, is looking at to look at this stuff. So that's what we're going to be working on today, is using clustering to build a dictionary so that we can take a variable-sized input where there's a bunch of features that are all over the place, and we can process it and get a fixed size vector that we can then stick into a classifier. So that's the whole idea. The technique that we're going to use is called vector quantization. Or vector quantization for short. I don't think there's any shorthand for that. So let's look at an example real quick of what you might, how you might use this. So the first thing you kind of do when you do vector quantization is you just take chunks of your data. And by chunks, I mean random chunks. So from this image, so we have this image of polka dots. And we take a bunch of random chunks from this thing. And these over here are just random chunks that came from somewhere in that image. And you could kind of look at this. This is chunks from this particular image. And you could say, okay, yeah, this is a dot that came from somewhere. This is the top of a dot. This is the side of a dot. The important thing is that we're not selecting any specific spot in the image. We're just kind of randomly grabbing pieces. And while that sounds kind of odd that you would randomly grab pieces, when you have a variable length sort of input where the images are different sizes and it has different things going on, you can't grab specific pieces because they won't exist in all images. So you have to kind of just shift around, grab a bunch of little segments, and use those. Now, this image over here, you guys can see these, right? Okay. We did the same thing. We grabbed a bunch of pieces. And then what we're going to do is we're going to build a dictionary from all those pieces. Now, if you have an image, one image, and you get a, what do we got, 100 some little segments there, and we got another image that's 100 segments. If we have 1,000 images, we can't make a dictionary of 1,000 times 100. That's just too big of a dictionary. That would be a giant dictionary. And most likely a new image, it's going to have some of those chunks in it, but it's not going to have the exact chunks. So what we're going to do with vector quantization is first we're going to chop up an image into pieces randomly. It doesn't matter where we get the pieces from. Then we're going to take all of those chunks from all of the different inputs, and we're going to combine them into a dictionary. And we're going to form that dictionary by taking all those chunks and clustering them. So we're going to take all of the chunks that are kind of, top of the dot sort of thing, and we'll get a top of the dot cluster. So this is like the mean of a bunch of images that were the top of dots. And then this one, we were going to take this one and probably combine it with, I don't know, this one, and we'll get the side of a dot somewhere. There's probably a side of a dot, maybe here, maybe here. And the same thing over here. We're going to take a bunch of these stripy pieces, we're going to cluster them together, and we're going to get some stripes. These stripes are flipped, oddly enough. They go this way on, I think there was a mistake in the book here. They go in different directions. But when you cluster, you're going to get a bunch of entries that are sort of just the pictures that are, or the little snippets that are going in that direction. So basically, the whole technique is going to be take the inputs that are variable length, inputs, slice them up, so in the case of images, we might take a 10 by 10 chunk of the image. We might take 100 of these 10 by 10 chunks just randomly all over the image. So we should have, if we have some, let's say we have m inputs, we'll have m by n slices. And then we're going to cluster the m by n slices into dictionary of size k. And that will give us our dictionary. Now, as a second step, once you have the dictionary, we sort of start again. We start with our inputs. And we select, we don't have to do n slices, we can, but the n here and the number you select down here can be different. This is sort of the evaluation side of things. It has to be some number, so let's do p slices at random. And then we're going to find cluster for each slice. So this is going to be for one input. So let's just say one input. And then we're going to build histogram of cluster. And this is our feature vector. And it has one entry per dictionary entry. So that gives us our fixed length feature vector for each of the images, and that'll work for both the inputs that you originally used and for new images that come along or new data items that come along. So this part of the procedure is how you build the fixed length feature vector. Fixed feature vector. And this part is more how you build the dictionary. Once you get the fixed length feature vector, you can do whatever you want with it. Now the images or the data items, whatever they are, have been transformed into a fixed length feature vector. So one thing we can do, and one thing often is done, is you take all your inputs with all your fixed length feature vectors, and you throw them into a classifier. And you classify them according to the type of image they are, let's say. What the what was in the image or something like that. And from there, you have a classifier. Then if a new data item comes along, you can transform that using this procedure to get a fixed length feature vector. And you use the classifier you trained to basically score it and see what the label would be for that new thing. So this process is called vector quantization. The first half before the classifier is really the quantization part, and then whatever machine learning bit you glue it onto, that's not really part of vector quantization, but it is often used together. Vector quantization on its own is generally not very useful. It's so that you can get things ready for another algorithm. So I got two things I want to show you. This first one is just a demo I put together, which hopefully will work. I only used two images in this particular demo. Normally you'd use hundreds of images with of a certain number of classes. Yes?
Just on the last, on the piece of paper you had.
Yep.
Feature vector with entry for each entry. Is that saying that the dimensionality of the feature vector is the same dimensionality as your dictionary?
Yes. So if your dictionary has 100 items, your fixed length feature vector will have 100 items, and they're ordered. So they're ordered in whatever the order the dictionary is. So if the dictionary is a set of words and it's a, the, there, the feature vector you generate will be the number of A's that are in the document, the number of thes that are in the document, the number of theirs that are in the document. And then sometimes you'll normalize, depending on what you're doing, you'll normalize so that the histogram is all the things are divided by the total number of words in the document or the number of slices you use or something. You can do some normalization. But yeah, it's the size of the dictionary that determines the feature length. Okay, so I just downloaded some images here. This is actually really similar to what you're going to do for homework 5. So I just wanted to show you kind of how this stuff glues together. Again, I'm not going to show you code because this is your assignment. So if I showed you the code, you'd basically have your assignment done. So I can read some images, and I get 2 images. This is just the images I grabbed. I actually downscaled them so that they were really big, and then the features became like, does this have a block of completely red? This is scaled, so we never get a block of completely red. This is scaled, so we never get a block of completely white. And now we're going to do, the first things we're going to do is, the vector quantization code is actually pretty small. It's slice up the images, run a clustering algorithm, and you're going to run it with a standard clustering algorithm. You're not going to write k-means. You're going to use sklearn k-means or something like that. we're not going to make you write k-means, unless I'm really wrong about what we wanted you to do in the assignment. So anyways, we take those two images, we slice them up. So I think I did 100, probably 100 slices for each. Now, so you can see that these are the unclustered bits of the images. So this is just, we took each image, we sliced up 100 pieces of it, and you can already see that the dot image is way different than the line image. If I had not been lazy, I would have grabbed a bunch more images that were dots and lines and been able to show you guys that the dictionary can have, even for different images, it can have, very similar sorts of things in it. Now I take all those images, the 200 images, and I formed what, 15 clusters for some reason. Did I really form 15 clusters? Let's see. Apparently I used 15 clusters. That's pretty small for image recognition, but these are, I don't have any data here. So, so what you get is a dictionary. And that dictionary is basically saying, there is, the first entry in the dictionary is probably from the dot, is almost certainly from the dot image. The third one's from the dot image. This one's from the dot image. This one, this one, this one, this one, this one. They're all from dot images. Then the line images are pretty obvious. But notice these things are a little fuzzy. That's because, remember, we've clustered a bunch of things. We took a bunch of the pictures, the slices, and clustered them together and then found the average. Basically, the center of the cluster is the average of all the pixels. And so these are going to be somewhat fuzzy. And that's okay. That's what we'd expect. So these things will be slightly off alignment of each other. They will be, different pieces. They'll be rotated slightly differently. Depending on what images you have, these are going to be very different.
So when we do the clustering, we break up, we take two images, for instance. What you did, you took two images, you broke it up into a bunch of pieces, and you put all of those pieces into a big bag, and then you did the clustering. Yeah, so
this here is the input to the clustering. And you would have, if you had a lot of images like we should, you would have thousands and thousands of inputs to your clustering. But in the end, you're going to have, the number of clusters will be much, much smaller. Like I took 100 chunks from each image, and I came up with 15 clusters. I probably could have done much less. In fact, I think I did 10 clusters the first time, and it worked just fine.
Does each cluster have a label assigned to it?
No. We don't know anything about the mappings of labels to clusters. We don't need to, because you're gonna chunk up the image, right? And then you're gonna cluster, and it's possible that you might have just taken a chunk from two different images that were from two different classes, and they looked really similar. And so you would put them into the same cluster. So there's no guarantee that all of the things in a cluster belong to all of the same image, or to all of the same label, more to the point. So the clusters, we don't know anything about what the labels are. And in fact, you can, one of the things that you can do is if you have, like, let's say you have a set of images, but you only have 100 of them labeled. But then you have a lot of unlabeled data. You can take all that those unlabeled images, chop them up and get little slices. Take the labeled ones, chop them up and get little slices. And then you could build a dictionary that is hopefully more general. Now, when you build the classifier later, you obviously can only use the labeled ones. But you, up front, can use way more data. Because the first part is unsupervised and doesn't matter what the labels are. All right, so we take these guys, these 200 things. We cluster them into 15 things. Now we're going to take the images and we're going to create the histograms. So basically I take a new image. This happens to be the dot image that I used before. I take a bunch of random slices again. I don't take the same slices as before. I actually take random slices again. And if I run this again, it'll actually change. It scrolled down, so it didn't really look like it changed. But I think that's changing. So now what you look at, this is the histogram that I was talking about. So this first cluster matched 2 random slices from this image. The second one matched none. The third one matched 2. The 12th one, this one, these are the cluster numbers, and it matched, the 12th one matched 5. And this becomes your feature vector. So your feature vector, literally for this image, would be this guy right here, which is just the counts of the different cluster matches. So the one thing to notice here is that because we used a pretty obvious thing, we can see that it got a lot of zeros where we have the stripy images, and it got a lot of non-zeros where we have the dot images. Here's the same thing for the striped image. Again, it's the opposite. Oh, I switched my clusters here. There we go. Now you see that, for the dot image, the dot image, the dot image, it actually does a pretty good job of saying, there's no dot-like clusters in this image, but there are a lot of line stripy parts to this image. So again, this gives you a feature vector. So at this point, you've quantized the images. And now the next part is how you would use them. So this is not technically the vector quantization part. This is just training a classifier. So I would take all of my inputs. I'd slice them up again. I would create the histograms to create a bunch of fixed length feature vectors. Then I would use those histograms as input to a classifier. So this first step just does exactly that. Now, I'm only using 2 images. This is a pretty easy task. But you can see, if you look at this guy, all I did was take the X training and the labels I knew, and I fit a Gaussian naive Bayes against those guys. And it spits out, the probabilities of, we could probably look at the probabilities of each of the clusters for a given label pretty easily. I mean, they're in here somewhere. I just don't know what the variable is. You can see that I did pretty good on this. My accuracy was 100%, and my test accuracy was 100%. Turns out it's really easy to do these images. If I had 50 images that had different alignment and different size dots and different colors, and I chose the colors pretty much exactly the same so that it couldn't just say red things are polka dots and blue things are lines. Although that might still be in there a little bit because I'm sure it's not the exact same red. But that right there is vector quantization. So this is what you're going to be doing for homework 5. Questions on that?
So when you build the histogram, do you have to slice up the input image?
Yeah, you re-slice the input image.
And then you compare with the clusters?
And then you take the dictionary of cluster centers. For each slice, you find the closest cluster center, which is, like any of the k-means will have a predict method, and it'll just give you back the cluster assignments. And that becomes your feature vector. I mean, it's like, it literally, all I did was, it's buried in Git histogram, so that's up somewhere else. But literally, it takes the cluster, the k-means clusters, and you do a predict if you're using sklearn, and it spits them back. Any other questions? Okay, so let's look at this. So your assignment is actually going to be this. You are going to get a bunch of time series data, and the time series data is taken from accelerometers it'll have like 3 dimensions, like it's X, Y, and Z, and basically people did activities while wearing the accelerometer. So, or holding it or doing something. I guess they could hold their phone and brush their teeth. And we just recorded that. Now, these waveforms have different lengths. Some of them are 6,000. Apparently, it takes a lot longer to eat meat than to brush your teeth. Some people brush their teeth for twice as long as other people. Presumably, the second guy doesn't brush his teeth very well. So you're going to need to do vector quantization on it. So same thing. You'll chop up the image, or sorry, you'll chop up the waveform into pieces. You'll take those pieces, and I think here's a bunch of pieces. That these are actually the clusters after you took all the pieces and clustered them together. In this case, we took a length of 30. So if you saw the time series data was somewhere between 1,000 and 2,000 whatever units it was, and we're only taking 30 of size of 30. So we're taking actually pretty small slices here. And you can see there's some very different patterns. There's some very long, slow patterns coming along. There's like a very rapid pattern. There is, a high magnitude rapid pattern. There's kind of a low magnitude rapid pattern. So those things are gonna be the cluster centers that you're gonna use. That when you get a new piece of data, you're gonna match those cluster centers and get your fixed length feature vector. And then from that, here's the histograms actually, where you can kind of see, hopefully, that like brushing your teeth and climbing stairs and combing your hair and climbing stairs have different looking histograms. Brushing your teeth and combing your hair actually have fairly similar histograms, but climbing stairs is completely different from those two. So you take these as your fixed length feature vectors, and you're going to stick them into a classifier. And I don't know that we had some classification something. He didn't label it, so I don't know what any of that means. Probably certainly not the accuracies. Yeah, I'm not sure what that graph is, so we'll ignore that. That graph doesn't exist. Okay, so that's your homework. That homework is really hard for some people. The reason it's really hard, and you can expect it to be somewhat hard, is because you have to glue together 3 techniques: the slicing technique, the clustering technique, and the last classification technique. And knowing, what data you have after each piece can be tricky. Now, it turns out once you do it, it'll probably look very simple. You'll go, okay, that's just, it's just a, sort of a transformation in 3 steps, nothing too complicated. But conceptually, it can be kind of tricky early on when you haven't done this sort of gluing together algorithms. So take a look at that sooner rather than later, which I say about all the homeworks, but that one does take people a little time, and I think we did give you 1.5 or 2 weeks or something. There's a little more time between 4 and 5, I believe. All right, last questions before we...
How would you say, how much would you divide the dictionary compared to the test or training data? Like, is there any fixed amount?
No, a lot of this, and I think in the assignment we ask you to do this too, a lot of it is just trial and error almost. The size of the dictionary versus the size of the pieces versus how many pieces you're going to classify with. I mean, you don't want the dictionary to be too big because that goes into the classifier. But classifiers can handle 1,000-dimensional fixed vectors pretty easily. So you don't want it too long, but the bigger the dictionary, the slower it is to do the match against that dictionary. Because remember, you have to do a pretty expensive, basically an n by k comparison of the dictionary to each of the items that you're going to do it. So you don't want too big of a dictionary, but you have to have it representative of all the stuff you're going to chop up. So that's really the key. As far as number of input items versus dictionary, I don't know that there's a big correlation. I don't know that I have recommendations for that. You try things is what it comes down to. If you have 1 million images, you probably want a dictionary of 1,000 at least. Probably way more actually. I would have to look at like modern neural nets to see how many like features they kind of are picking out to even get an idea of how big the dictionary should be. With images, you actually use, you can use really small, like 5x5 or 7x7 blocks to do image recognition, and that actually works really well. For these particular homework, I think it probably has some recommendations in the text, but I don't know. Okay, so that was vector quantization. That was the easy part of today. Now we're going to do something called expectation maximization. Also known as EM. If you've taken a stats class, you've probably run into EM, especially if you took a higher level one. It's a really common technique that people use. Now we're going to talk about it in terms of using it to generate clusters. But it's a general algorithm that you can use for a lot of different things. EM will come up again and again in different areas. So EM is a probabilistic approach. And for clustering, we're going to use what's called a mixture of Gaussians. So if you have a bunch of points, when we cluster them, we're going to figure out not only where the centers are, so those centers are there and there, we're also going to figure out sort of the shape of the Gaussian. So when I draw lines around a Gaussian, these are just sort of the contours where they all have the same value. So you can think of it that the probability is going down with each line. And the same thing with this guy. You'll have some set of lines that are sort of the fixed probabilities. So just so this makes sense, this is maybe highly probable, maybe 0.9. This is 0.7. This is 0.5. That's not how Gaussians are shaped, but they drop off like a bell curve. But it's kind of from how you view it, it's going to look like that. Now what we're going to do is it's a mixture of Gaussians. So we're going to have multiple Gaussians, but we're also going to have a weighting term, which says that, say, 90% of the data points fall into this guy, and 10% fall into this guy. And that's going to say sort of like a new data point, even if it's fairly far from the center, might get put into this cluster because this cluster gets way more data. So we'll define that a little more formally in a second. Now for what we're going to be talking about, we're going to make a really strong assumption that will simplify our math. And that's that we're using a unit covariance on our Gaussian. We're going to talk about the multivariate normal, which is what a Gaussian is, in a second. But we're going to use a unit, basically zero covariance among the different things. That means all of the Gaussians are going to be circles. And they're going to be the same size, which those aren't drawn the same size. But these are the same size, just trust me. It's the way the paper's leaning. So they're going to be the same size because they're going to have a variance of 1 along all of the different things. And this means that we aren't going to be able to cluster easily something that looks like this, or anything that looks like this. And this, again, EM can do that. There's no problems with doing that. It's just it complicates the math of doing the algorithm quite a bit if you include the variances. Now, if you run an EM algorithm from a package, they support this. They'll figure out what the variances are. There'll be non-zero covariances, so you can make things that are ovals that are ellipses that are twisted, that sort of thing. But that means, well, let's look at the multivariate normal, just the math of it, so you guys can see. So multivariate normal is just basically a Gaussian that you've taken to multiple dimensions. So if you think about it, a Gaussian's normally a bell curve. In 2 dimensions, now we have a bell, in a 2-dimensional shape. And in higher dimensions, you'd have a hyperbell. And the formula for the Gaussian is just, if x is a vector, we're going to have a set of means, and we're going to have a sigma, which is basically the set of the covariance matrix. So there's a big long formula here. It's 1 over the square root of 2 pi to the dth, which d is the dimension of x and of u, times the, that's in the determinant of sigma. So sigma has to be positive definite in order for this to work. Just like any of our covariance matrix, they're basically diagonal. They're diagonal, and so you can flip them, and they're the variances are along the axis there, or along the diagonal. Now the formula here looks just like the Gaussian, except that we take it and we extend it out to use vectors. Let's transpose, and then we have sigma 1 over sigma inverse times x minus mu, and that should be right. Okay, so that's going to be your formula for the multivariate normal, which is usually just called a Gaussian. Now the expectation of some x is going to be equal to the mu's, and then the sigma is the equivalent of the cov mat that we've calculated before. So that's kind of the multivariate normal, and that's what we're going to use to actually do to model each of the little clusters of data. So if we want to estimate these parameters, if we have some data and we want to estimate these parameters for a multivariate normal, we use maximum likelihood. Just like we use maximum likelihood to estimate any probabilistic parameters, basically you count up the things and get the most likely thing. So this is just the means of x is calculated by the summing up all the x's and then divided by the number. And then the sigma squared is equal to, it's equal to sigma. That's the sum, not the sigma for sigma. Where'd it go? Okay. And this is, you have seen this before. This is just the outer product divided by n for all the data points. So that's how you would estimate it for the multivariate normal. Now if we if we rotate and scale this, basically if we make the assumption that we are using zero covariance with a unit variance among the elements, which is the assumption we're going to, what's up?
Why does the segregate not have a hat?
Because I missed the hat. There is no reason. Yeah, it should have a hat. Yeah, so I got completely thrown by that. Oh, we're going to make the assumption that sigma is basically the identity matrix, right? So variance 1, no covariance. They're going to be circles, basically. If we do that, then the, why did we use U? The probability of a x given 0 mean and some identity, the identity matrix for sigma, is going to be equal to some constant, which we can figure out the constant, but we won't keep writing it out, times the e to the, that should be an x, over 2. So this is just dropping it into the here. We chose a 0 mean. We dropped it into there. And if you do the multiplication, you can end up distributing this out. So if there is no covariance, the multivariate normal becomes a product of a bunch of individual normals. So this one would be the first keep doing U. The first element squared. And then this guy would be the second element squared. Here this is the component, not the data item. Out to the exponential of the dth component squared. And the constant is going to be a bunch of things multiplied together too, the different things. So basically the multivariate normal breaks into nice pieces if you have 0 mean and you have identity sigma, so the cov map. So that works out pretty nice. We'll probably take advantage of that later on because we're going to make those assumptions, and it actually makes a lot of things easier. There's still people writing. Put your hand down if you're writing. Okay. One person did it. Okay. All right. So when we talk about forming clusters or using probabilistic methods to create clusters, probabilistic methods are often described as generative processes. So we don't talk about we have a bunch of dots and then we put them into clusters. We talk about we have some probabilistic formulation and then we sample from that probabilistic formulation to get our dots. So that's sort of how the data, we assume the data has been generated. So what we mean by that is a mixture of Gaussians, which is what we're going to be using. Mixture of Gaussian, same thing as mixture of multivariate normals. Gaussian multivariate normal is going to be the same thing. We're going to have, just like k-means, we're going to have k clusters, which means that we're going to have k multivariate normals describing the data. We're going to have a mean for each k, so there's going to be 1 to k of these. Now, because it's a multivariate normal, the size of any given mu is going to be d. So these are actually, there's k of these mu's, and the mu's are dimension d. And now here's the thing that makes it a mixture of Gaussians. We're going to have a bunch of things that we're going to call pi 1 decay. These are scalars. And we're going to use J a lot for the cluster. If we add up all those scalars, 1 decay of them, we will end up with 1. So they're basically just a probability distribution. And they represent, like I mentioned, the probability that a point came from a given cluster. So the generative process we're going to talk about is, first thing we're going to do is we're going to look at these, the pies. And we're going to say, okay, we want to sample from the pi distribution to find the cluster of this data point we're going to generate. So we look at the thing, we roll a die, it comes up with, whatever, so that it's in the 4th cluster. And once we know what cluster it's in, we will look at the multivariate normal associated with that cluster. So in our case, we'll look at the mean, and we'll sample from that multivariate normal to get a data point. So let's say if we knew the means were this guy, and this guy, and we knew that the pies were, let's say, 0.1, 0.3, and 0.6, because they got to add up. So I roll a die. I get a, let's say we get 0.2. That means it's going to be in this cluster right here. We sample from this with the mean of wherever this is, and a identity covariance, and we get a point right there. We repeat this. It ends up in this cluster, and we sample, and we get a point right there. Then we probably get another point. We get a point. We get a point. And we're just generating the data. And the assumption is this is how the data was generated. And so you end up with this cloud where it's going to be fairly round. And it's going to be, most of the data is going to be around this guy. Some of the data is going to be around this guy. And a little of the data will be around this guy. So the mixing probabilities, those pies, kind of control the size, a little bit of the size of the blob, or the size of the cluster. Now the multivariate, the variance could also control that size a little bit, but we're assuming a variance of 1, so instead we're going to use that mixing parameter to say, many more of these things come from here. And that does mean one thing. So if we have 2 clusters like this, and we had a dot, let's say we had, this is a 0.1, and this is a 0.9, it's very possible that if we get a data point right here, that it was generated from this cluster, because 90% of the data is generated from this cluster. Even though the probability of it being in that multivariate normal is much, much higher than it being in this multivariate normal, this mixing probability is going to say, yeah, well, it's really more likely to be in the multivariate normal on the left, but because of the mixing, because 90% of the data came from the multivariate normal on the right, it's going to often be from that multivariate normal on the right. Does that make sense? Any questions on that? That's kind of a little bit of the magic of clustering with EM, is that the generative process that assign these data points is going to can cross the clusters with each other. Now, in the end, we're going to figure out the cluster probability for each point, and we'll still go through the same process. So it's possible that these clusters could overlap, but in all likelihood, the clusters won't overlap that much. It'll move the means when we learn the thing. It'll move the means around so that they're not really overlapped. But that's part of the learning. So we probably wouldn't get this sort of situation, but it could happen. All right. All right here. So in order to do the clustering here, we're going to have to estimate 2 things. Now we're going to be given we're going to be given some data, X. That'll be a bunch of data points. And from that, we have to estimate both the mu's for each of the k parameters and those mixing probabilities for each of the k clusters. So we're going to take X, figure out what the likelihoods of all the different things are, and that's where we're going to get the mu's and the pi's. Now, if we were doing this in a real EM algorithm, a real EM clustering algorithm, where we could have variances or covariances that were non-zero, you would also have to learn the covariance for each multivariate normal, and that's a whole nother bunch of math that we're not going to go through. But any good EM clustering algorithm will do that for you and give you clusters that are not sort of aligned and circular. All right, so we know what we need to do. Given X, we're going to try to figure out pi and mu, the pi's and the mu's. We're going to use a maximum likelihood, just like we do for any time we really need to learn parameters for a probabilistic thing. So if we look at just the likelihood of the log likelihood of the data, so this is the log likelihood. Now this is actually just the log probability of the data, given the parameters. We end up with something like log of p of xi given mu's and pi's. Now, in general, we're going to call this set of things theta. It just means all of the mu's and all of the pi's. And the reason we do that is just for notational reasons. It's just writing out mu and pi 1,000 times is a pain. Now, normally when we do maximum likelihood, we would take this, we'd try to do an optimization on it, so we'd end up taking the derivative, set it equal to 0, then use something to either analytically or heuristically figure out what those parameters are. Now, it turns out that when you take this, first of all, this is a sum of a log of what ends up being a sum inside of there. So you get this sum of log of sums that you'd have to take the derivative of. It's intractable. We can't do this. So our standard techniques for finding the maximum likelihood isn't going to work. However, if we assume our generative process that we talked about, we know that the mu's are the means of the points of the Gaussians, and we know that the pi's just are the number of points over the total number of points in any given cluster. So pi will just be, if there's 50 points in cluster 1 and there's 1,000 points total, then whatever 50 divided by 1,000 is, which I probably could do somehow. But we don't know what those numbers are right now. If we knew those numbers, we could calculate them. But we don't really know which points belong to which clusters. We don't know where the means of the clusters are. So now we need a technique to do this, to figure that stuff out. So, okay, this EM gets very math heavy. Some of you guys will just kind of glaze over. In the end, what happens is the math is really complicated up front. You work out all the math for the probabilistic sort of, the probabilities of the multivariate normals and the mixing probabilities. And in the end, you come up with a fairly nice, concise formula that you apply. So some of you might just want to skip all the math and go to the formula. That's fine. It's somewhat important to see how we go through the process of working through EM. But in all likelihood, nobody here will do EM from scratch, do the sort of probabilistic formulation of EM from scratch, unless you go really far into the sort of the statistical ML sort of side of it. It's just very hard, and it only works for certain distribution combinations, and it basically you can, EM will work for a lot of different distributions, but working through the math for any given distribution is really complicated. So it works for things other than clustering. So the gist behind EM is basically let's assume that we knew some, so this is kind of the high level EM. Let's say we knew the sigma at time n. So what we're going to do is we're going to work through figuring out, basically given that current state, what's a new state that's basically, what's a new set of thetas that are good, that are basically better than the old thetas. So it's going to be an iterative process. Much like k-means, basically we're going to move the means and the mixing, and then we will recluster, figure out what goes where, and then we'll move the means again, and we'll just iterate back and forth. And those two steps are called expectation and maximization, and that's where the name comes from. So let's just assume we have this theta for the nth iteration. And we're also going to assume a second thing. EM works because you take this delta, which is called a hidden variable. Variable. It's a hidden variable in that we don't know its setting. So it's a random variable. It follows some probabilistic distribution, but we don't know what that is. And that probabilistic distribution we can write out to be P of delta given some theta, we'll write theta n, and the input data. Now the role of the hidden variable is to make the figuring out the math a lot easier, to make it the different probability distributions tractable to calculate. But we don't know the hidden variables. So let me give you an example. When we go back to EM clustering, the delta, the hidden variable, is going to be the assignment of, for each point, which cluster it's assigned to. So basically the delta is going to say, the delta 1 is going to say, point, the first point is in cluster 5. Delta 2 is going to say the second point's in cluster 1. And if we knew delta, we don't, but if we knew delta, it's very easy to calculate all the probabilities. Because, rather, it's very easy to calculate those parameters, theta, the mu and pi. Because, again, if we knew where the points were, it would be easy to do those calculations that we talked about a second ago. Now, of course, we don't know the deltas. They're hidden. So we got to figure them out. And actually, we never really figure them out. What we do is we take an expectation over the deltas. So this is there's two steps that go into EM. This first step, which is called the E step or the expectation step, we define a function. And basically the function is theta given the old theta, whatever our current iteration is. And it's the expectation of some loss function with respect to whatever the hidden variables are. And that's why it's called the expectation. So if we write out the expectation, we iterate over all of the deltas. We take the loss, that's the likelihood, of theta. We take the data and delta, which is, because we're iterating over delta, this will be set. So this is, again, this is easy to calculate because once we know the data and we know the hidden variables, it's trivial to calculate theta. That's important. Like I said, EM works for a lot of distributions. This has to be calculable. You have to be able to calculate that in order to do this, given the hidden variables in the data, which for a lot of distributions, it's trivial given these hidden variables. In the end, you'd set it up so given the hidden variables, it would work. And then just to finish up the expectation, we need to take the probability of any given delta given the current set of thetas and the input data. So basically that second part is just definition of expectation, but you're saying for each possible delta, what is the probability that that delta is the correct delta, is the actual delta that existed. So what you're doing is you're really walking through every possible setting of the deltas. You're evaluating the parameters that would come up for that particular setting of delta times the probability of that delta. And that will give you the Q function. Now, a couple things to look at. This is fixed, the Qn. That's our current iteration. This theta is a variable. So this function is a function in the variable theta with a fixed theta n. That's going to get a little confusing if you see theta n or pi with the n on top. That means it's a fixed value we already know. If it's just a theta or just a pi by itself, that's a value we don't know. So the second half, or the second step of EM is called the maximization step. So this is where we take n plus 1, and this is just the argmax of theta of the Q function of theta given the theta n. So this is the expectation step, and this is the maximization step. So basically, you take this function we defined, you look at all possible thetas, and you come up with the most likely theta given that function. Now, of course, you don't look at all possible thetas. That would be impossible because it's probably an infinite space. So we're going to work through a bunch of math to figure out which thetas are actually exists. So that's kind of the basics of EM. Now you iterate back and forth just like in k-means, and eventually you'll get to a point where the mu's and the pi's aren't moving that much, and that's when you're done. Now, as I mentioned, this is a general EM is a general technique. It can apply to non-clustering, all sorts of non-clustering problems, and it does. It's used extensively in statistics. We're going to apply it to clustering, which next Tuesday we're going to take this and we're going to plug in our multivariate normal, our mixtures, and all of the things we know. We're going to assume that the deltas are the assignments to clusters, and we'll go through all the math to figure out, what is the efficient way to calculate this step and this step for clustering. And that's going to be kind of what EM clustering is. It's the, once we run through all the probabilistic machinery, what is the actual calculation that comes out? And the actual calculation, there's a bunch of summations and a bunch of matrix multiplication, but in the end, it's really, you kind of assign a weight to each point going to each cluster, and then you move the cluster centers. So it becomes a lot like the soft k-means that we talked about on Tuesday, where really points are assigned to multiple clusters with some mixing probability. That's exactly what soft k-means was. The way that you generated which cluster soft k-means, the proportion that a point belonged to each cluster, is going to be much different than the way we do it for EM, but it will be conceptually the same. I think that's all I got for today. The next part is going to be a ton of math, and I don't want to jump into that at the end of class. I'm not saying you shouldn't come to class on Tuesday. You should. This stuff's good to see, but it will definitely be math heavy. We're starting to get into the math heavy part of the course, so just be prepared for that. What was that? Just a second, guys. Number 2? This is n. Oh, yes, there's a +1. Yes. I mean, I guess it's an n++ if you're talking about, programming.
What's the difference between like this colon or semicolon and this?
Okay, so the semicolon is often used with likelihoods. Generally, it means it still is pronounced given, but it generally means that sum isn't going to add up. It's not a probability distribution, and it's not going to add up to 1. So if you think about it, the likelihood of data is sort of the sum of all the probabilities of the data. So those probabilities can be as much as 1, as low as 0, and then you sum a bunch of them. So the sum is not going to be a probability distribution that sums to 1 over all possibilities. So really, it's just sort of an indication that it's pronounced given, but it's an indication that this isn't a probability distribution. It's still, we're looking at these parameters specifically, we're calculating it based on these parameters, but it's not a probability distribution.
So whatever comes after it is a parameter, but
yeah, it's sort of a fixed parameter. Just like probability, it's like the probability of x given theta means that if we had theta, we can calculate x. Likelihood is the same way. If we had x, we can calculate this other whatever we're calculating. It's just that it doesn't necessarily add to 1. So all you can do is compare them to each other. You can't say it's a probability distribution. You can just say this likelihood is less than this likelihood.
okay.